All right, everyone. I am here with Joseph Soriaga. Joseph is Senior Director of Technology at Qualcomm. Joseph, welcome to the TWiML AI podcast.
Great. Yeah. Thank you for having me. It's great to be here.
Looking forward to jumping into our conversation. We'll be talking about a couple of very interesting papers that you and your team have that will be published later in the year at Globecom. Before we dig into those, though, I'd love to have you share a bit about your background. Tell us how you came to work in the field of machine learning.
Yeah, sure. I'd be happy to. So I've actually been working for a while in wireless. And when I actually started in coding and information theory a while ago, even and well before the deep learning revolution. But there were some interesting parallels, I'd say, with machine learning, because at the time it was really exciting, where belief propagation was very popular, and it was essentially being used to achieve Shannon capacity in a lot of different use cases. And the trick was, trying to find the right graphical model for the particular problem to achieve that. This is coming from turbo codes and rediscovery of LDPC. Another nice parallel was that our kind of community was getting used to and embracing a lot of like experiment driven research, like really extensive, you know, coding up of experiments to prove something could work, because it was very difficult to prove rigorously and mathematically that this belief propagation would achieve Shannon capacity. But through a lot of extensive experiments, you could go and simulate it and design things, and then for all practical purposes show that you were achieving it. There were a lot of relationships to machine learning and belief propagation at the time, but I was really more on the communication side at the time. And then, coming out of school, my PhD, I joined Qualcomm corporate R&D, and that was where I was really uh, excited and exposed to this industrial research. And one of the great things about Qualcomm is that they not only invest substantially in research, but it's a very open, collaborative environment where we would really focus on taking a fundamental research idea and then proving it out, see how far you can go and making the system more complicated, more realistic, and to the point where you're actually going to build it and test it and demonstrate it. And that's been kind of a core philosophy that they've continued to do through, I don't know, my 15 plus years at the company. So that's kind of been a great thing. I through that course touched a lot of different things on the system, like the base station, the modem, the entire air interface system, and then most recently at 5G, worked closely with the research and then coming to participate in standards. So I did a lot of work in that, and through the course of that, I'd say it's 5G is of course very amazing things have opened up in this technology, new frequencies, new spectrums, new paradigms for how we do things, new services, of course. Um, and through that, we started to see that we have this very large bandwidth. We have lots of directionality now with millimeter wave, um, and the system itself becoming lower latency, more precise. It actually is very sophisticated for understanding the environment too. So positioning was one of the first, interesting use cases of trying to understand the environment that the 5G system, was able to demonstrate with these really large antenna arrays and wide bandwidths. And so, as the system gets more complicated and the capability of the system also grows, it just became more obvious that like there's a lot that can happen with AI and wireless, and so I kind of over time transitioned to doing much more AI in this space, as opposed to being more wireless driven, and that was kind of one reason to moving more directly into Qualcomm AI research. Another important motivation I had was that um, this air interface, it actually does help accelerate the developments in AI and the ubiquity of certain applications. So because at the start it just is a better link to the cloud. Things can be more interactive or more direct, and but then over time, as the devices also become more capable and we start moving more of the lower level perception tasks, for instance, locally to the devices, then it enables like the next stage of AI. So the cloud can concentrate on the more complicated and emerging research advances, like understanding reasoning and generalizing beyond what has been trained on. And so it's very natural to think, okay, let's get more involved in this and ride the kind of the next wave of where things are.
Yeah, what I'm really looking forward to digging into in this discussion is what I think of as the other side of the AI 5G coin. Specifically, I spoke not too long ago with your colleague Ziad about how 5G can be used to accelerate distributed AI applications. That was episode 489 back in June. Uh, but we'll be talking about here again, the flip side, the ability for machine learning and AI to help enable 5G and make it more efficient. You mentioned in your introductions Shannon capacity. That's kind of a key concept that flows throughout your work. Would you like to take a second to explain that?
Yeah, sure. The Shannon capacity is, this is one of these amazing results from Claude Shannon is um, being able to characterize how well, for a particular channel, conveying information from a transmitter or receiver, how well can you hope to achieve, throughput um, without actually, building a system to do it. And then it becomes a question of like, exactly what do we do to build the system to achieve that? And one of the really important advances from Shannon was that we know when to give up and to focus on different things, because if it's beyond the capacity, we shouldn't bother and move to the next problem. But if it's well within the capacity, um, then we know that what what potential is there and what we have to realize. So
Yeah, so kind of the theoretical bandwidth limit,
exactly, yeah,
let's say between two communication devices or entities, I guess.
exactly. As the channels become more complicated to characterize, some of these principles, they could become more difficult to evaluate. To some level, you start doing Monte Carlo integration, and then some level, this is where machine learning can start to come in and help us to understand what's the best representation for this particular system, which has now become so complicated um, to really get the right heuristic and the right abstraction. So that's how things have evolved.
One of the papers that we'll dig into, or the first of the papers that we'll dig into, is one on deep learning based network augmentation. Can you introduce that topic to us? We spoke to your former colleague Max Welling about that about a year
Yeah,
ago. At the time, it was kind of this interesting idea that was being pursued in research. It sounds like it's matured quite a bit in a year, and now you've got a paper about some of the results you're seeing.
yeah, yeah. I'm glad you brought it up. So yeah, last year Max did bring up this topic, and the importance of it in communication is that so the idea of neural augmentation is you want to, whenever a particular problem has some abstraction where we have a good algorithm that's perfectly matched to that abstraction, there's no reason to change that algorithm anymore. But if the abstraction itself is a little mismatched with reality, we can augment that algorithm with some neural network so that we can make the right adaptation of the algorithm for the mismatch instead of kind of redesigning the whole thing. And there's still ways to make that, say, end-to-end trainable with the real world. So one really nice benefit of this that plays well with the communication, academic community and industry is that there's a long history of abstracting different problems in wireless and domain where we know that we're doing exactly the right thing, and it's just a matter of now how do we adapt our domain knowledge now that the channels are becoming even wider bandwidth or even higher frequency, and there's more nonlinearities being introduced or um, more sophistication in the model itself that we weren't really able to capture properly in our abstraction. And so this is where that idea of the paper is coming in.
And the idea there is that, what we often see in academic papers relative to kind of real world deployment in many fields is that the papers, out of necessity, in order to get clean mathematical results, will simplify the real world, ignoring any number of factors. And what this work is suggesting is that deep learning can be used to kind of map the simple models to what's seen in the real world to make them more to make them match better and ultimately kind of more predictive. Is that the idea?
Yeah, that's right. To make it more predictive. Actually, in the paper, what's interesting is, um, initially we were just naturally it's thinking that okay, this is so we were trying to track a channel, and then the speed at which you move, it affects the Doppler of that channel, how fast it's changing, and if we know the Doppler, then the dynamics are well suited to the Kalman filter in one particular example. So it's just a matter of making sure we have the right parameters for our Kalman filter for that particular speed that we're at. And
And so when we're talking about Doppler, we're talking about the communication between like a fixed base station and a moving
yeah,
um, communicator, like someone on a mobile device in a car, and you're using the Doppler shift to kind of localize that device.
yeah,
Is
exactly.
that the general
That's
idea?
that's one
Okay.
one example. Surprisingly, Doppler is everywhere. So wireless. The
Okay.
nice thing about wireless is you get great coverage because it bounces off a lot of things. And sometimes transmitter and receiver aren't moving, but they're bouncing off of things that are moving. And so then we get
Okay.
Doppler again there. So it is a very ubiquitous problem that we deal with. Even when I'm talking to you today, if we're on a cellular system, we'd have to deal with that to some degree.
And so when you talk about channel tracking and Doppler and all that stuff, like why do we care? Why do you care? As a someone who's building systems to help people communicate.
Yeah, good question. So we always want to, like coming back to that Shannon capacity, we always want to operate at that Shannon capacity. And so it's evolved in our systems to track this channel so that we know don't put too much information if the channel is not very good. And then if the channel is really good, let's put as much information as we can and opportunistically, ride the wave of when it's good and when it's bad. And this is really
And how does that tie to Doppler?
uh, Doppler, the dynamic of the channel helps us to be able to predict how well. And then when we're actually trying to decode the signals themselves, we'll be able to um, resolve some of that signal better once we know how the channel has rotated through the course of time. And so those are the two aspects of it. And in this particular paper we were citing, we were looking more at the tracking of the rotation so that we can resolve the signals that have been
Mhm.
degraded.
And when you say rotation in this instance, are you talking like phase shift or
Yeah,
something
like a
like that,
phase shift.
or
Yeah, probably using a lot of jargon, but exactly. We'll send our communication signal. Usually, your message that you want to convey goes through a very sophisticated remapping of bits into constellation and a MIMO transmission across antennas, and that's the signal that we're trying to get to the receiver. And then we want to be able to decode that original set of points that convey the message. And if that gets through, then we can always remap that back to the original information that was to be
Mhm.
conveyed. So,
Yeah, so maybe to kind of try to recap the setting here, going back to this Shannon model, you've got this transmitter. The transmitter is pumping information into this channel. There's a receiver that's trying to capture as much of that information as possible and kind of maximize the bandwidth or throughput in this channel. And there's inherently this assumption of a noise source that's like disrupting the communication between the
mhm.
two. I think we kind of think of, as lay people, a straight line between a cell tower and a
Yeah.
mobile, but as you've talked about, the signals bouncing all over the place. Even if it wasn't bouncing, you just talked about MIMO and these other technologies. Really, there's multiple signals or channels kind of between the cell tower and the device, and there's noise being inserted. The signals are all going different directions, and the idea is that you have to figure all that. You The more you can kind of take the information you're getting about the network and the devices, Doppler and all this stuff, you can use that to ultimately kind of statistically predict what was sent at the device and vice versa. And that's how you maximize the your bandwidth or throughput.
Yes, I think you put it well. Yeah, exactly.
Got it. And so, you know, Kalman filter. Where does Kalman filter come into play in all this?
Sure. The way the channel is evolving, this you fade up and you fade down. It's very well modeled in some cases, in a lot of cases, by an autoregressive model. And then a common filter is a very um, a well studied and optimal way of tracking that dynamical system. And so that's where kind of that solution has come into play.
Got it. And so, kind of going back to this idea of neural augmentation, talk about the kind of the gap between the Kalman filter and what's observed in real world.
Sure, sure. So in the real world, you're going to move, or things around you are going to move at different speeds, which implies that your Kalman filter um, should be using parameters for each speed, nominally. That would be the best thing to do. And so like a very natural, first attempt at this problem is you have a bank of Kalman filters and you have a bank of speeds, and then you have a two-part problem. What speed are you at? And then once you figure that out, what Kalman filter should you use? This is a it's a very simple, nice, intuitive, but it's a two-part problem, and it's also doesn't necessarily scale as well because you have to go and train all this whole bank, and then you have to figure out exactly. You can't have an infinitely you know um, resolved bank, so you have to figure out what kind of bins are you going to have to cover what you need to cover. And the other, so it's very natural, and you look at how people can just have deep learning try to solve the system. So you can remove the Kalman filter and say, okay, we have to deal with Doppler and Kalman filter changing. Why don't we just put an RNN in the system and then train it on all this data of the channel changing, and then have it figure out what it should be doing. And it is a universal approximator, so if we give it the right amount of data, it should figure out to do what the Kalman filter does, right? So
And specifically, would you be using the RNN to predict the channel characteristics or to predict the ultimate output bits, for example?
oh, just the channel itself, and then we would feed that into
Okay.
the rest of the demodulator that would get the bits in. Yeah,
Okay. Got it.
yeah, and
So again, kind of universal approximator, given enough data, an RNN should work. But
But
I think
yeah,
is where you were going.
exactly. Yeah, but what we the other thing we tried was let's just have an RNN to take the observations and then tell us what kind of Kalman filter we should use. And then, the nice
Mhm.
thing now is we have somewhat of a continuum of parameters for the Kalman filter, and then we also can still have a nice way of making it end-to-end trainable. So, unlike the two-stage approach where you have to go and um, have some kind of heuristic of training things and building up different parts of the system, here we have one that we just give data to it and then let it train. And and so we tried all these, and the nice there were some interesting things that actually came up. So naturally we want to see that we're doing better than everything, and we were able to show that this what we're calling this neural augmented Kalman filter. Specifically, we're calling it a Hypernet Kalman filter, since we have an RNN that's setting the parameters. It's kind of a Hypernet. And then interestingly, so the benefit over the traditional approach is that it's end-to-end trainable, so it's much more straightforward. You can just expose it to data, and then it learns, and then it's ready to go. It makes the offline process much simpler, and it ends up being also because there's a continuum of settings. You're not um, limited by the coarseness of binning that typically comes up from practical uh, reduction of the problem of the solution. Now, when we look at how it compares with the LSTM, which is what we used in this particular solution, one thing that was really interesting was that our Hypernet Kalman filter actually addressed unseen cases a lot better. And so um, one important detail I didn't want to get to earlier, but what happens when we're actually tracking the channel is that we don't um, we don't get to we usually use pilot symbols, so something that we know at the transmitter and the receiver, we send it, and then we use that pilot to figure out what the channel looks like, the fade and the phase shift and so forth. And that the frequency at which we send a pilot um, is a trade-off we always have to deal with. Like if we send more, then we have a great look at the channel, but we don't have much information that we can send. And if we send less, the opposite. And so one interesting thing was when we had the LSTM train on one particular pilot density or frequency at which we send these pilots, and we gave it a different density, one that was higher or one that was lower. It didn't just perform worse, it actually, in some cases, was somewhat significantly lower in performance. And so it was, seemed like it was probably learning some things that would help it to track the particular case it was given for the training set. But yeah, but maybe he was using maybe the wrong features or is overfitting in such a way that it was not good at generalizing. Whereas when we constrained it to be this Hypernet Kalman filter, it actually performed well. Like it gracefully degraded when it went to, um, well, actually did well when it went to this lower density or this higher density without having seen these in the training set.
And so the two cases we're comparing here are the LSTM
Mhm.
alone to predict the channel versus the model that's predicting the common filter
That's right. Yeah,
characteristics.
that's right. Yeah.
And the idea maybe is that in a sense, it kind of relates to this conversation I have in the podcast a lot. Like we know a lot about the physical world and its behavior, and we've developed these models that are representative. In this case, the Kalman filter. So how do we couple kind of statistical approaches and physics-based approaches so that we're not kind of throwing out the baby with the bathwater, right? And in this case, it sounds like the common filters providing some constraints or guardrails to the RNN that allow it to perform better even when it's uh, or to generalize better.
Yeah, exactly. I think that's well put. Exactly the point of what we're doing. And we tried other situations where not just the pilot density changed, but even the strength of the signal to noise changed. So we could train it at one signal to noise ratio and then test it at a lower one or test it at a higher one. And we saw again a similar robustness from having a Hypernet Kalman filter versus just a pure neural network.
Mm-hmm. And this idea of what you're calling neural augmentation or hypernet augmentation, are you applying it to, or have you applied it to other types of models or other problems?
Yeah, I think that yeah, it's a great that you brought that up. I like to think of this particular paper and all the things also from a podcast a year ago with Max. This is kind of a seed idea, and we wanted to really go deep in one particular problem so that people can see the different trade-offs that we were trying to understand and see how things were doing. Um, but then it's not that a common filter is going to solve every problem, but there are going to be these other core algorithms in different problems, and we want this philosophy of don't forsake all the domain knowledge you've built at this point. There's really just a little bit of mismatch. You have to figure out what that is and put the neural network such that we give it the right amount of flexibility to learn how to adapt, but not too much that it might learn the wrong things and kind of adapt the solution the wrong way.
Before we jump into the next paper, can you speak specifically to the results you saw with this? You kind of spoke generally to it. It performed better than the LSTM alone, but how did it perform relative to the original Kalman filter implementation?
The original, like the classical solution where you kind of classify bin, um, that one, the shortcoming is more in how coarse the bins are, and so it's a very nice smooth degradation now, or I should say smooth interpolation across these bins because we can't in the classical approach we can't quite just have a very fine resolution of speeds of from 0 to 500 kilometers per hour. We have to somehow make that practical and do a dozen bins or less. And so there's a lot of trial and error or a lot of heuristic behind solving that. Um, and the HyperNet actually is able to give us a different way of having like almost a continuous interpolation there. And that's really where we saw a nice healthy gain over that.
Got it. Got it. Awesome. Awesome. So the next paper we want to talk about is focused on RF sensing and communication. Introduce us to the setup here and the problem that you're trying to solve.
Yeah, yeah. This is kind of a fun area, I would say, because so I kind of walked you through the idea that signals degrade, environment interacts with the signal going from the transmitter to receiver, and we have to be able to track that well and deal with it so that we get the information through efficiently. Um, one interesting, the dual of this kind of is that um, the environment interacts and it can degrade our signal and it hurts the information that we send. But at the same time,
Hmm.
there's a lot of information about the environment when it's degraded the signal. And so then, oh, how much can we learn about the environment whenever it degrades the signal? It becomes like a question that we want to get to. And now when we
Hmm.
go to 5G, we have like much larger antenna arrays, much wider bandwidth. It's like a richer signal set now that we have to really understand how things are being interfered with from the environment to the communication system. And so we flip this around and we say, well, instead of trying to get the information through, let's try to learn what's in the environment as much as we can to see, what can we, how far can we go with this essentially. And so, in a very simple, the very starting point where they both interact, is that can we try to predict when the fate is going to come and go, and then, very simply like that. But as you may have seen, even industries are, like small companies are starting to introduce this. There are different, other levels of more sophisticated inference that can be done, like understanding the presence of a person, in a particular space, or the activity of, detecting an activity in a particular space. Um, there has been gesture recognition. I believe that you've probably seen this on phones and other places. And then, a location and position is another very interesting use case, where it's, called RF fingerprinting sometimes, where you actually try to pinpoint where the activity is happening, relative to the environment. And
I assume all the gesture stuff was based on sensors in the phone, like, camera or LiDAR or something. It never occurred to me that they might be using RF interference to track gestures.
yeah, that's that's more recent, I would say, relatively speaking. But there's a technology. As you move higher in frequency, you can actually separate the transmitter from the receiver in a very small space. So a phone can transmit and receive without jamming itself too much. And that's the technology behind some of the recent gesture recognition. So a phone will transmit at a millimeter wave frequency and listen at the same time, and then from that it can see signatures of things moving. And then of course we apply machine learning to figure out, is that signature, a swipe left or a swipe right, or
Oh
that
wow,
kind of thing.
wow.
Yeah.
And you mentioned some other companies working on this. A couple of years ago, back in February 18, I did a interview with a company called Ariel that is in this space, like using Wi-Fi in the home or commercial buildings to detect presence and motion, and if in an elder care scenario, if someone falls, that kind of thing. It sounds like that's the same kind of problem or same kind of result you're tackling. What's different about the work that that's in this paper?
Yeah, great point. Yeah, so a lot of, really nice use cases, to our knowledge, are, supervised and very densely labeled. And so, which is a great solution, but it's not necessarily something that scales. So what we did here was, the team came back to the problem, and they asked, is there any way we can reduce the requirement of labeling? If we can make it completely unsupervised with the proper loss function, or if we can have some weak labeling. And we looked at, instead of looking at, all the problems in the space, we looked at, positioning. So it seemed like a pretty challenging problem, but at the same time, a really nice one that, has a lot of commonality with other, applications of RF sensing. And so there was a prior result where, since you know that what you're tracking is moving in time, they looked at using a triplet loss to try to space things out, so that in the latent space, so in the real space, we can kind of assume that samples are close together because they're close in time. And so in the latent space, we, it should be that they're also close in the latent space because they were close in time. And then, in these previous results, they had a nice first step in showing that, okay, we can get a reasonably good, similarity between the latent space distance and then the real distance in the real world. But it wasn't, perfect, because it wasn't, geometrically consistent. So, a floor plan may not look like a floor plan, even though, you are moving around, and close distances were close. the part that was missing is that sometimes you may be close in distance, but not necessarily close in time because you may have walked in a circle or you may have come back somehow to the point that you were at. So our team looked at clustering. So a lot of deep cluster, really interesting technology that's been used for other things in self-supervised learning, and looked and say, what if we put triplet loss together with this deep cluster so that we can address this problem when we do come back to the same space, that we know that okay, they actually should be close together and not far apart because of they're clustered in another dimension. And so putting those two together, now our latent space, which looks a lot better, a lot closer to reality of distance and position than before, than previous methods before. And so now you can go and just, in theory, you just walk around a room and then you're just listening to all the RF signals, and with the loss functions and so forth, training it, you come back and you see, okay, the latent space looks a lot like the room and where you were in the room. And it's not perfect, but it's a lot better than previous by doing this, both this triplet loss and then this clustering. And then our team went one step further and they said, what if we just coarsely told you, okay, you're in a room and the room has this shape, and then you move to another room and the room has this shape. So it's still, now it becomes labeling, but it's a much lighter labeling. Instead of having some way of annotating exactly where this um, person was moving around the room, you just tell it, okay, I'm in a room, I'm moving around, but the room has this boundary, and that's all I'm gonna know. And then, the really cool thing was that now they actually could get to, within 1 or 2 meters, which was as good as the supervised case where we did have a very precise tracking of the user in the labeling. And so by putting all these things together, then the idea is that it's very simple to go and build up a neural net that can infer where you are from the interference in the RF that it sees.
Hmm. And so the two parts of that are the triplet loss and the clustering, the deep clustering. That's fully unsupervised, and then the what you described there towards the end of
Oh, that like
kind
zone
of
labeling, I should say.
localizing in the
Yeah,
room, zone
yeah,
labeling. That's the weak labeling part.
that's right. Yeah, yeah.
Got it. And were those done successively, or were those done? Was the system trained with kind of two components to the training process? This unsupervised part and the weak supervised part.
It was done together. So there is one, I should say, if you read the paper a little bit further, there are some things we do to initialize one other loss function that we put in just to jumpstart it. But overall, those two key parts we're doing together.
I should mention that there's a video of this system
Oh, yeah.
that we'll post a link to in the show notes page. It was demonstrated at MWC, Mobile World Congress. Is that right?
Yeah, yeah. Thank you for reminding me. That's right. One of the really exciting things about this was we had a whole team that could give us real world data and then different locations, and we can really prove out these ideas. Is this how robust is this an approach? And although the paper and the demo probably showed two particular types of layouts, we did test among more, and also the situations within each layout were also played around with, like someone holding a metal sheet, for instance, and so if you go to that MWC demo, you can get a nice feel for what it how does it look. They have a nice animation of a person walking around, which is the ground truth, and then you can see where, like, a dot to tell you where should you be, and it's pretty amazing thinking that. Unfortunately, the MWC doesn't quite tell you that it's unsupervised or weakly supervised, which I personally feel is like even more amazing than
Uh
even the
huh.
idea of like you're being able to be tracked with just RF signals is amazing in its own right, I think. But then
Yeah.
when you go a little deeper and you realize, oh, this is something that they've gone and made it, much more scalable in a sense. That's really like amazing that the team was able to do that.
Yeah, and I've wondered in thinking about these applications, like, do you to what degree do you need kind of inside access to the devices or the Wi-Fi access point in the case of if Wi-Fi is the signal that you're using in order to do this, or is there some net flow or logging or something I can turn on in my Unify system that will collect all the data, and I could try to replicate what you're doing and build some system that tracks presence within my building here.
There are some standards activities happening to make this somewhat, I guess, like a standard that's accessible. I think we mentioned that a little bit in our paper. Um, I know that, so I can't speak on like our product and other products in the field. I don't know that very well, but I do know that there are these capabilities, and we've had the benefit of working with those like we have counterparts on like the wireless research team, and they really help us to enable us to get the right data and clean up the signal and make sure. So, um, in theory, you should be able to do some of these, I think, but the actual execution, I have to have another show with some other experts to give you that tip.
Awesome.
Yeah,
Awesome. Maybe to kind of wrap things up, these two papers are again kind of under this theme of how machine learning can be used to enable you know the, the more effective delivery of network services like 5G, um, and in some ways a lot of that is enabled by increasing sophistication on of the devices themselves, and machine learning capabilities on device. I'd love to hear you kind of riff on where you see all that going and what's possible.
yeah, yeah. I should say that when when you see this demo at MWC, it's part of I would say like a series of 4 or 5 demos in machine learning and 5G. And there's a lot of really cool applications across like for instance like there's outdoor positioning, there's millimeter wave beamforming, there's efficient channel state feedback. A lot of these have core designs in enabled from deep learning, and they are also relying on the device having a very capable AI, and that's been a core you've probably seen on the show from many of our Qualcomm participants. We're focused on making sure that uh, what AI can do, it becomes ubiquitous, so we can bring it to mobile and have it in as many places as we can. And it not only are the use cases that we come to associate with AI, like not language processing or computer vision perception, but even making the wireless system better also is now benefiting or potentially going to benefit from having a very capable device. And in this area of say joint RF sensing or using the COM system for RF sensing, um, this is like other things I talk about. It's this very simple example, and it's a seed idea, but there's certainly more things that can come from it. And we didn't demonstrate it on devices, mobile devices. We actually demonstrated on base stations. But you can imagine that there are other things that you can have the mobile device get involved. And building up an awareness of the environment. Here, where we're showing that you can track people, you can imagine over the course of this that you can start understanding your environment and um, making the whole communication system more efficient, because now you don't have to, for instance, you don't have to blindly search for where's the base station coming from, or where's the best direction to have a communication link, because you've established an awareness of where strong reflectors are, where blockers are, and where you're moving in the environment. So that's something we're really excited about moving forward to see this joint interaction between sensing helping to communicate AI and sensing helping communication, and then AI on device helping this enable this.
Hmm. Awesome. Awesome. Well, Joseph, thanks so much for joining us and sharing a bit about what you're up to and walking through these two papers with us.
Great. I hope you enjoyed it, and hope you look forward to seeing more stuff that we're going to do because we have a lot more coming. It's really exciting place to be right now.
Awesome. Thanks so much. I certainly did.